let's talk about giving nature's best materials superpowers. Not in a comic book, but right inside a chemistry lab. Today, we're diving into how scientists are giving two amazing natural substances a serious molecular makeover, upgrading them for the future. So we're starting with something you'd find in nature, a silkworm cocoon, and through some brilliant chemistry, we're ending up with an advanced hydrogel. That's a high-tech material that could one day be used to build new tissues or deliver life-saving drugs. It's where nature's genius meets human ingenuity. So let's meet our two main players. On one side, you've got Silk Fibroin, or SF for short. This is the protein that makes silk so incredibly strong. And on the other side, we have Hyaluronic Acid, or HA. This stuff is all over our bodies, and it's an absolute champion at holding onto water. Both are fantastic on their own, but we're about to see them join forces. So what's the big mission here? It's to give both of these materials a brand new superpower, the ability to connect and build a structure just by being exposed to light. The fancy term for this is making them Photo-Cross-Linkable. And trust me, that's a huge deal for things like 3D bioprinting, where you need to build things with absolute precision. All right, let's get into the nitty-gritty. First up is silk. How exactly do you take the fiber from a cocoon and turn it into a high-tech polymer that you can control with light? Well, it's a three-step journey. First, degumming, which is basically a fancy word for boiling the cocoons to wash off all the sticky stuff. That leaves you with pure, pristine silk fibers. Next, you dissolve those fibers, turning them from a solid into a liquid solution. And then comes the magic step, methacrylation. This is where the real chemical upgrade happens. Methacrylation sounds super complicated, but the idea behind it is actually pretty simple and really clever. Imagine you're attaching millions of tiny molecular handles all over the silk protein chains. At first, these handles just hang out, but they're designed for one specific purpose. When you hit them with UV light, they snap together, linking all the individual chains into one solid network. So how do they actually attach those handles? They use a special chemical tool called Glycidyl Methacrylate, or GMA. You mix it in with the silk solution, and the GMA gets to work, attaching those handles. The end result is a totally new molecule, SFMA, which is our original silk, but now it's fully equipped with its new light-activated superpower. Okay, that's silk. Now let's switch gears to our second hero, hyaluronic acid. It's gonna get a very similar upgrade, but with its own unique recipe. Let's see how scientists hack this natural moisturizer. For hyaluronic acid, the goal is exactly the same: add those light-activated handles. But the chemical toolkit is a bit different. Here, scientists first use some other molecules to kind of prime the HA, and then they bring in the final tool, something called AEMA, to attach the handles. The process is a little different, but the outcome is the same: a modified HA that's ready to go. Okay, so this is the crucial question, right? After all this mixing and reacting in the lab, you've just got a clear liquid. Everything is happening at a molecular level that you can't see. So how in the world do you know for sure that you actually attached all those invisible handles? How do you prove the makeover was a success? Well, the answer is a really cool technique called spectroscopy. It basically lets scientists look at the unique molecular fingerprint of a substance. So by comparing the fingerprint before the reaction to the one after, they can see exactly what changed. It's like molecular forensics. And here's the evidence. Let's play a quick game of spot the difference. On the left, you see the NMR spectrum, the fingerprint of the original silk. Now look at the right, the modified silk. See those two new little spikes that just pop up out of nowhere around 5.8 and 6.2? That's it. That's the smoking gun, the unmistakable fingerprint of our newly attached handles. But hey, good science means you need more than one piece of evidence, right? So now we're looking at a different kind of fingerprint called an FTIR spectrum. Here you can see how the shape of those big dips, what they call the amide peaks, has changed. This confirms that the underlying chemical structure of the silk has been altered. It's more proof that the makeover worked. So, what about our other hero, hyaluronic acid? Well, if you look at its NMR data, it is the exact same story. On the left is the original HA, and on the right is the modified version. And there they are again, those same telltale peaks, right where we expect them. This proves that the AEMA tool did its job perfectly. And for the final piece of evidence, check out the FTIR fingerprint for the hyaluronic acid. This one's maybe the clearest of all. See that new little peak that appears around 1640? That's the undeniable signature of a new chemical bond that was formed during the modification. It's an open and shut case. The handles are attached. We can actually put a number on this. Scientists can calculate something called the degree of methacrylation, which is basically a success score. It tells you what percentage of the possible attachment points actually got a handle. And look at these numbers. Over 41% for silk and over 32% for hyaluronic acid. That's really efficient. It proves the makeover wasn't just successful, it was highly successful. Okay, so we've gone through all this incredible chemistry just to stick tiny handles on molecules. You've got to be asking, so what? Why does any of this matter? Well, this is where it all comes together. And here is the payoff. Now that they have these handles, you can mix the modified silk and the modified hyaluronic acid together. Then, with just a quick flash of UV light, click, all those handles lock into place. What you get is a stable, structured gel that combines the strength of silk with the moisturizing power of HA. You've created a brand new composite material. And having that level of control unlocks some incredible possibilities. We're talking about creating advanced scaffolds that could literally guide our cells to grow into new tissues. We're talking about printable bioinks that could, one day, be used to 3D print entire organs. This technology could lead to smarter wound dressings that help us heal, or drug delivery systems that release medicine exactly where and when we need it. It really makes you think, doesn't it? The biggest medical breakthroughs of the future might not just be discovered out in the wild. They're going to be engineered, designed, and built right in the lab. By performing these molecular makeovers, scientists aren't just making new stuff. They're literally building the toolkit for the future of medicine, one molecule at a time.